we understood that the electron in the outermost shell, say for in this case, this is the space in which the outermost electron exists or occupies. The amount of force that it feels is not the same as the ones inside it. Now, this is because of shielding effect and all of that we kind of got introduced to. So the next question is, what factor influences the effective nuclear charge? The obvious one is the number of proton, right? More the number of proton, stronger the pull. Next is the core electron. What does it mean? Well, if we go back to this, if we are looking at 3s as the outermost electron, the core electron is all of this. But if you are looking at, say, this as the outermost electron, okay, 2p's, right? Then the core electron will be 1s2 and 2s2. Take a minute, think about it. If electron occupies the p's, the p region, right? Before that, we have subshells of 1s2, 2s2. Those are your core electron. It's as simple as that. One before that, okay? Now, it depends on the core electron. More the inner electron or the core electron, okay? This is also inner electron, more the blockage, more the shielding. So the most simplest formula, actually it's not this simple, but for now we'll take it to be this. That is, the effective nuclear charge is equal to total proton minus the shielding that is done by the core electrons. Now, how does this vary across the different atoms? Of course, we'll make use of periodic table, right? So when we are moving from left to right in periodic table, the effective nuclear charge increases while we are going along a group, down the group. There's a slight increase, if not, it will stay the same. So when you're moving from left to right, there is significant increase. Well, when we're moving from top to bottom, a slight increase, if not, it remains the same. So visually, I can put it across to you guys in this manner. Okay, so this is your hydrogen, helium, lithium, beryllium, boron, so on and so forth. We're looking from the other side, like we're standing over here and we're looking at it. So that's the perspective. So you can see how things are varying. Okay, so you can see it from here: hydrogen, helium, lithium, beryllium, boron, so on and so forth. So from this end, it looks like this. Okay, what happened? Yeah, something like this. Can you see the pattern? Left to right, a significant increase from across the length, right? Like, one length. Let me do that. Yeah, in this manner. Okay, I'm not able to do that. So you guys got it along the length, along the column. There's not so significant changes what they're telling. Of course, scientist. That's been the pattern. Now, why do certain group exhibit variation while the other remains constant or consistent? The reason is, when we're moving from left to right on a periodic table, ZD increases because the proton increases while the shielding, that is the inner electron, will not change. It's as simple as that. When you're moving from left to right, the number of inner electrons will not change. So while the number of outer electrons are increasing, but the shielding effect will remain the same, while the number of proton will increase. That is, when I move from left to right, left to right, the number of protons is increasing, while the inner electrons will not change. Okay, so when I'm moving from 5, 6, 7, 8, and so on and so forth, the inner electrons will remain the same. The shielding or the core electrons will remain the same. So the number shielding effect, right? This formula is there, is it not? Where is it? Okay. Oh, sorry, I went ahead. Yeah. shielding, this value. This particular value, the core electrons will not change. And because of that, when you're moving from left to right, we see a huge increase. Down the group, there will be slight increase or stays the same because more energy level means more shielding. That is the inner electron also changes down the group, right? That's evident with this actually. Is it not? 3D and it remains 3D till this point. Okay. And then 4p comes, so on and so forth. But we have seen that how 3D and all of this energy levels are kind of close and so on and so forth. There are quite a few factors, but yeah, the simplest way to understand this is when you're moving from left to right, the core electrons remains the same down the group. The number of core electrons also changes, and so there is slight increase. Now, can you select an element that is an atom and compare its effective nuclear charge value with another element in the same period, that is the row, and the same group? So let's do that. We'll consider carbon. So carbon is, let me show it over here. Carbon is over here. Okay. And the other one which we are picking is oxygen and silicon. So oxygen is over here and silicon is down. So carbon is the base, comparing it with oxygen and silicon. So carbon's value is 3.2. From left to right, we have oxygen. It jumps to 4.6. Silicon, which is down the thing, just below that, it's 4.2. Again, these are approximate value, but you're getting the idea. Okay. Now, does the nuclear effect value indicate the carbon 3.2 has a stronger hold on its outer shell compared to the silicon? Whatever value we saw over here. Does it tell that carbon has a better grip than silicon, or is it the other way around? Well, since a higher effective nuclear charge means a stronger positive pull from the nucleus on the outer electron, it is actually that silicon has a stronger hold. So basically, indirectly, what the question is talking about is, or trying to teach you is, more the value, right, more the effective nuclear charge, more the attraction, stronger the pull. That's what I'm trying to conclude over here. Okay. So now that we have understood valency and effective nuclear charge, we are ready to talk about electronegativity and the other related concepts as well. So this was a bit too much. Let me recap. So what factor influences that pull that the external electron experiences? It depends on two things. One is the number of protons, and another is the number of core electrons. The simplest formula of effective nuclear charge is total protons minus the shielding effect by the core electron. And effective nuclear charge, it varies in such a way is that in a periodic table, if you're moving from left to right, it varies significantly. Down the group, it's increasing, but not to that extent. The question of why does it happen? It's common sense. If you're moving from left to right, the number of core electrons does not change, but the number of proton increase. And so the shielding value will remain the same while the number of proton increases. So obviously, if A is increasing while B remains the same, if I have A minus B, right? If A is increasing while B remains same, what happens? Overall result will also increase, right? While down the group, this increases and the shielding also increases. So the net effect is that the resulting force, it's okay. It's almost the same. That's the funda over here. Now, as an example, we took carbon, oxygen, and silicon. Carbon and oxygen are down. Sorry, left and right, my bad. Carbon is left of oxygen. And so we can see a significant jump. While silicon is down of carbon, there's a jump, but comparatively less. And one last thing is, higher the value, better or stronger the pull is what I'm trying to point out here. And using all of this, we'll be able to understand quite a few things in the future.